In this presentation, I will be focusing on certain terms in volumetric analysis and certain calculations in this chapter. In the definition of volumetric analysis in simple terms is using titration as the method to determine a concentration of an unknown using another substance with a known concentration. There are two main types of titrations that you will learn. Firstly, they are the acid-base titration, which involves neutralization reactions, and secondly, the redox titration, which involves a redox couple. However, in this presentation, I will be focusing on acid-base titration. The first definition that I would like to share with you is the equivalence point, also known as the stoichiometric point. It is the point where the stoichiometric amounts of the reactants have reacted. The reaction will have just completed and only the products will be present. This point is independent of the indicator that you have used. For the acid-base titration at the equivalence point, the pH must change sharply so that it can be identifiable using an indicator. An indicator is used because the solutions in acid-base titrations are colorless, and we will need an indicator to tell us that the neutralization reaction has been completed. In addition, as indicators work over a range of pH, the stoichiometric point cannot be pinpoint located, but can only be identifiable. Indicators are still nonetheless important because they are used to help us tell when the reaction has reached completion. The indicator's color change work over a range of pH, and this is what we know as the working pH. The color change indicates the end point of the titration. This table is important. The choice of indicator will help you to determine the end point of the titration. In addition, the end point of the titration need not be the equivalence point of the complete neutralization reaction between an acid and a base. The next definition we will talk about will be that of the end point, the point of titration where the indicator changes color. We will have stopped adding titrant and the volume of the titrant is therefore recorded. In the ideal case, we would like to have the visible endpoint to coincide with the equivalence point. However, for acid-base titration, generally when we choose an indicator, it should be one that shows a color change very close to the equivalence point. This is because the working pH of the indicator is over a range of pH, and hence it is not going to be exactly at the equivalence point. In order for us to understand how we make the choice of indicator to use, it is important that first we understand a little bit more about titration curves. So titration curves help you to aid the understanding to the choice of the indicator used. First and foremost, a gentle reminder, the working pH of the indicator is the same as the range of the pH which the indicator changes color. Now, the titration curve will show a sharp drop in pH, indicating the completion of the titration reaction. This sharp drop explains why indicators will change a color change at the end of the titration. Do note that when we pick an indicator, the pH of the equivalence point must be within the range of the working pH changes of the indicator. Otherwise, we would not be able to detect the end point of this titration reaction. In the titration curve, we can't pinpoint where the end point is shown. However, we will only be able to determine the equivalence point. In addition, the exact curve that you see in the titration graph can only be obtained when we use a pH meter or a data logger. Note that not all equivalence points pH will be 7. We will teach you more in the topic of ionic equilibrium. Now, sodium carbonate is a diacidic base. It's a base that has to accept 2 replaceable hydrogen, whereas HCl is a monobasic acid that donates 1 replaceable hydrogen. The purpose of showing you the sodium carbonate against HCl titration is to highlight to you how the choice of the indicator with its corresponding color changes will help you to determine which is the equivalence point of the titration reaction. We notice that sodium carbonate reacts with 2 moles of hydrochloric acid because sodium carbonate is a diacidic base while hydrochloric acid is a monobasic acid. When phenolphthalein is used, its working pH is between 8 and 10, hence it coincides the first equivalence point of sodium carbonate. Hence, at this point, 1 mole of sodium carbonate reacts with 1 mole of HCl. When Meta Orange is used, its working pH is between 3 and 5, and that coincides with the second equivalence point of sodium carbonate. Hence, 1 mole of sodium carbonate will react with 2 moles of hydrochloric acid. Therefore, when we use phenolphthalein and Meta Orange as indicators, we will obtain different volumes of HCl at the end. This curve helps us to understand why, and you can see from this curve that when you use phenolphthalein as the indicator, you will need half the volume of HCl used as compared to when Meta Orange is used as the indicator. Once again, this exact graph can only be obtained when a pH meter or a data logger is used. Next, we will talk a little bit more about acid-base titration, which is also known as your neutralization reaction. Neutralization reactions can be represented by the following 2 equations. The first equation, you will learn more about it in ionic equilibrium. Basicity of an acid refers to the number of replaceable hydrogen atoms in one molecule of acids. For a monobasic acid, such as hydrochloric acid and ethanoic acid, a dibasic acid will be one that has 2 replaceable hydrogen atoms, and an example will be sulfuric acid. And tribasic acid, an example would be phosphoric acid. A tribasic acid would have 3 replaceable hydrogen atoms in one molecule of acid. Well, basicity of acid refers to the number of replaceable hydrogen atoms in one molecule of acid. Acidity of base refers to the number of replaceable hydrogen atom one molecule or ion of base accepts. Now, when you do acid-base titration, the common thing to do is calculations, and there is a strategy to perform these calculations. We often use mole ratio in the calculations. Taking the ratio of the reagent as shown by the following formulas, this is how we obtain the calculations of our unknown concentration of solutions which titrations is supposed to find out. Our first example would be 25.0 cm³ of sodium hydroxide required 10.0 cm³ of 0.1 mole per dm³ solution of sulfuric acid for complete neutralization using phenolphthalein as the indicator. Calculate the concentration of sodium hydroxide in moles per dm³. Now, in this question, we will have to adopt several steps. First thing, it is very good to write the equation of the reaction. This is because it gives you the mole ratio between the reagents. Naturally, sodium hydroxide being a monoacidic base and sulfuric acid being a dibasic acid, what happens here, they will react in a ratio of 2:1 to form us 1 mole of sodium sulfate and 2 moles of water. Next step, you will be able to calculate the amount of sulfuric acid used, and this step tells you how much amount of reagent you have used from the burette. So what happened here is, the amount of sulfuric acid used will be the volume of sulfuric acid used multiplied by its concentration. Calculate the amount of sodium hydroxide neutralized. This will tell you the amount of reagent that is found in the conical flask. The amount of sodium hydroxide in 25 cm³ is 2 multiplied by 1.00 times 10 power minus 3 to give us 2 times 10 power minus 3 moles of sodium hydroxide. This we can obtain because for 1 mole of sulfuric acid, it reacts with 2 moles of sodium hydroxide. Hence, the amount of sodium hydroxide in 25.0 cm³ is twice the amount of sulfuric acid being used. We can then calculate the number of moles of sodium hydroxide in 1 dm³. That is actually the step that help you to calculate for the concentration. So, concentration of sodium hydroxide is simply the number of moles of sodium hydroxide divided by the volume of sodium hydroxide that amount of sodium hydroxide belongs in. Usually, we mention that the sodium hydroxide is taken from a bulk solution. Hence, dilution factor may be required to take into account to calculate the final concentration of sodium hydroxide. But in this particular example, there is no need to do so. The second method makes use of mole ratio without statements. In some sense, there are multiple steps involved, as first and foremost, we will have the equations, and then the mathematical steps which require you to apply mole ratio formula and solve the concentration of sodium hydroxide using the following steps. Another common example that we use titrations for is largely for back titrations. Back titration happens when you have a known amount of excess reagent A that is added to a reagent B. What happens here is the amount of excess A that remains unreacted by reagent B can be determined by a form of titration. The titration will tell you the excess amount of reagent A, and by subtracting the excess amount of reagent A from the initial amount of A added, the exact amount of A that reacted with reagent B can be determined. And that will help us to find out what is the amount of reagent B that was initially found in the conical flask. An example of back titration calculations would be the following. Fa1 is a mixture of sodium chloride and sodium hydrogen carbonate. Fa2 is a solution containing 30.0 grams of Fa1 per dm cube. 40.0 cm cube of 0.2 mol per dm cube of hydrochloric acid is added to 25.0 cm cube of Fa2 in a conical flask, and the excess acid remaining in the flask required 21.60 cm cube of 0.150 mol per dm cube sodium hydroxide for complete neutralization. Calculate the percentage by mass of sodium hydrogen carbonate in Fa1. It is important for you to identify the reactions that's taking place. There are two reactions that's taking place. Do note that sodium chloride is neutral, so it will not react with hydrochloric acid. So the first reaction is when your sodium hydrogen carbonate reacts with hydrochloric acid. Your hydrochloric acid is in excess. So therefore, this excess hydrochloric acid will be reacted with sodium hydroxide in a back titration manner for you to find out how much excess hydrochloric acid is present, and therefore finding out how much hydrochloric acid is used to react with sodium hydrogen carbonate. So the mathematical steps firstly includes calculate the amount of sodium hydroxide in 21.60 cm cube solution. So the amount of sodium hydroxide present will be just simply the concentration of sodium hydroxide used multiplied by the volume of the sodium hydroxide. We will be able to therefore calculate the amount of excess HCl remaining in the flask, which will simply be the same as the amount of sodium hydroxide we have used, because both HCl and sodium hydroxide reacts in a 1-to-1 ratio. Calculate the amount of hydrochloric acid that is reacted with sodium hydrogen carbonate in 25.0 cm cube of Fa2. That we first will require to calculate the initial amount of hydrochloric acid used. We have used 40 cm cube. Multiplied by its concentration, we will be able to obtain the initial amount of hydrochloric acid in 40.0 cm cube solution. The amount of hydrochloric acid reacted with sodium hydrogen carbonate will simply be the original amount of hydrochloric acid minus the excess amount of hydrochloric acid to give us 4.76 times 10 power minus 3 moles. Therefore, we are able to calculate the amount of sodium hydrogen carbonate in the flask, which will simply be also 4.76 times 10 power minus 3. That is because sodium hydrogen carbonate reacts with hydrochloric acid in a 1-to-1 ratio. Finally, we will be able to calculate the percentage of sodium hydrogen carbonate found in Fa1. First and foremost, we will need to calculate the molar mass of sodium hydrogen carbonate. Once we find out the molar mass of sodium hydrogen carbonate, we can find out the mass of sodium hydrogen carbonate in 1 dm cube of Fa2, which will just simply be 15.99 grams. The percentage of sodium hydrogen carbonate in Fa1 will simply be 15.99 divided by 30 multiplied by 100%. My second example of back titrations will be the one that we talk about. A sample containing ammonium sulfate was warmed with 250 cm³ of 0.800 mol per dm³ of sodium hydroxide solution. After the evolution of ammonia has ceased, the excess sodium hydroxide was neutralized by 85.00 cm³ of 0.500 mol per dm³ of hydrochloric acid. What mass of ammonium sulfate did the sample contain? There are two reactions once again taking place, and they are: first, your ammonium sulfate react with sodium hydroxide in a 1:2 ratio. Then, the excess sodium hydroxide will react with hydrochloric acid in a back titration manner for you to find out how much excess sodium hydroxide was present, and therefore you can find out how much sodium hydroxide has reacted with ammonium sulfate, and therefore you can find out what is the amount of ammonium sulfate that is found in the sample. So our first step is to first calculate the amount of hydrochloric acid required to neutralize the sodium hydroxide. It is the amount of hydrochloric acid, which is the concentration of hydrochloric acid multiplied by the volume of hydrochloric acid. Now this amount is equal to the number of moles of sodium hydroxide that is found in excess as well. Calculate the amount of sodium hydroxide that reacts with ammonium sulfate, which is the initial amount of sodium hydroxide in 250 cm³, which is 0.800 multiplied by the volume of the sodium hydroxide used. The amount of sodium hydroxide that reacts with the ammonium sulfate is simply be the original amount of sodium hydroxide that you have minus off the excess sodium hydroxide. We will get 0.1575 moles of sodium hydroxide. We will therefore be able to calculate the amount of ammonium sulfate that has reacted with sodium hydroxide, and that will simply be half times 0.1575. That is because for every 1 mole of ammonium sulfate, you will require 2 moles of sodium hydroxide. Finally, we will be able to calculate the mass of ammonium sulfate found in the sample. It will be simply the molar mass of ammonium sulfate, when you calculate it first, multiplied by the number of moles of ammonium sulfate found in the sample. That will give us the mass of ammonium sulfate found in the sample. That's the end of this video on volumetric analysis. Thank you for watching.